Welcome back. In this video, we're going to continue with Chapter 7 and our review of thermodynamics. And now we're going to look at the third law of thermodynamics. And remember back in the chapter on the kinetic theory of gases, we saw that temperature was directly related to the mean kinetic energy of the system. So as the temperature went up, the mean kinetic energy went up. The temperature went down, the mean kinetic energy went down. So thermodynamic temperature has an absolute zero, which would imply that when you reach absolute zero, you have a mean kinetic energy of zero and no motion is happening at all. Now, that has consequences in thermodynamics. If all motion stops at 0 Kelvin, then that means that no energy can be transferred out of that system as work or heat. So the third law, developed by Walter Nernst, states that the entropy of a system approaches a constant value when its temperature approaches absolute zero. So we would expect then that as we get closer and closer to zero, it becomes more and more difficult to extract out energy in the form of heat or work. And so we get to a situation where the change in the entropy as we approach zero goes to zero. All right? Now, another way that Nernst stated this was to say that it's impossible for any process, no matter how idealized, to reduce the entropy of a system to its absolute zero value in a finite number of operations. In other words, it takes an infinite number of adiabatic and isothermal steps if you were going to try to reach absolute zero. So you can't do it in a finite number of steps. Max Planck actually took it one step further, and he stated the third law this way. He said that the absolute entropy of a perfect crystal vanishes at absolute 0 Kelvin. So instead of defining that the change in entropy goes to zero, Max Planck said that the absolute entropy of a pure substance in its pure crystalline form is going to be zero at 0 Kelvin. And to get into a full explanation of why Planck came up with this definition of the third law would require us to go into statistical thermodynamics, which we'll talk about in the next chapter. But for now, we're just going to take Planck's statement as just being related to the fact that in a perfect crystal, there's a high degree of position or orientational or an orientational order in a crystal. Okay, so this is sort of three ways in which the third law is stated. This is the strongest one in terms of its constraints, which was given by Max Planck. Now, in terms of the third law, then, and particularly Max Planck's definition of third law, then we would have a perfect crystal at absolute zero with perfect order, orientational and translational order would be throughout the crystal. But actually, trying to obtain such a state from a pure substance is not very likely, because as you try to cool a system down, a lot of systems are going to have some kind of frozen in positional or orientational disorder in them. Now, some systems you can cool down and they can get very close to a perfect crystal, but for a lot of systems that's going to be a little trickier. So there'll be some kind of configurational disorder that gets frozen in. So as an example of that, imagine trying to cool carbon monoxide molecules. We know carbon monoxide molecules have electric dipole moments, so there's a minimum energy configuration that we would expect them all to line up in some kind of perfect crystal like this here. But in fact, actually, what would probably happen is that you would, as you try to cool it down, you would end up in some non-equilibrium state where some of them are going to be flipped and they'll have slightly higher energy configuration. So this kind of situation, from a practical point of view, means that as we get colder and colder, we're not going to be able to reach a perfect crystal where the entropy is zero, but we'll reach some non-equilibrium state where we'll have locked in some kind of residual entropy. And this picture here also just, it's just a simple picture, but it also ignores the fact that there's also going to be isotopes that are present. So there will be carbon-13 isotopes that are around a very low percentage, but they'll be present, and the distribution of carbon-13 and carbon-12 isotopes is also going to add to that type of residual entropy that's present in the system. All right. So with that given, then, we can say that the entropy of a pure substance at any temperature, desired temperature, can be calculated by just doing an integral of the heat flow into the system from 0 Kelvin all the way up to the desired temperature. So that entropy at a given temperature, say TF, is going to be given by starting with the residual entropy at 0 Kelvin, and then any kind of heating that you would do from 0 Kelvin up to that temperature, and this is the heat capacity as a function of temperature. And then, of course, if there's any phase transitions along the way, whether it's the sublimation or fusion or vaporization, then you'd have to include that entropy change too. Adding all that together would give you the total entropy, absolute entropy of the substance at a temperature that you in this case TF here, whatever temperature you desire. So if you were doing this experimentally, then what you would say is that all you need to do is just look at the heat flow into the system, and you would just have to integrate that heat flow going into the system as you heat it up, going through these phase transitions, and then you could measure experimentally what the entropy of the system is. When you get to very low temperatures, however, it's very hard to do these heat measurements. Oftentimes, people will use the Debye theory, which comes from StatMech, to approximate the heat capacity at these low temperatures. And that has a form that looks like this, where A is some substance-specific constant, and then it varies as the temperature to the third power. So now that we know that we can calculate absolute entropies using the third law, then we can combine that with what we know about the thermodynamic potential. So for example, the Gibbs energy potential, and we can calculate the Gibbs energy change for a chemical reaction using the enthalpy that we know, particularly the enthalpy of formations, and now these absolute entropies. So for example, if I have a reaction I've written generically here with A plus B going to C and D with the respective coefficients here, then I can calculate delta G for that reaction from the delta H of the reaction plus the delta S for the reaction at a given temperature. And the delta H's we can calculate, as we learned earlier, from the formation enthalpies. So that would just be the expression that we saw earlier here. Now I'm just doing products minus reactants, including the formation of all the substances. Remember that the substances that are in their elemental form will have a delta H of formation of 0. So just remember that from freshman chemistry probably. So this would give us our delta H of formation. And now with absolute entropies, we could similarly calculate the entropy change for the reaction using the molar enthalpies, absolute molar enthalpies of the products minus the reactants using the proper stoichiometries there. Once we have these two, we can calculate the delta G for the reaction and determine which direction is the spontaneous and which direction is the impossible direction for this reaction. Okay, so that's it for this video on third law entropies.